Hello, so we're going to continue with the bonding unit, but now we're going to dive into covalent compounds. So we've already talked about ionic compounds and the polyatomics and variable charged ions and binary compounds. And now we're going to start talking about covalent compounds, or specifically covalent bonding. So when it comes to covalent bonds, again, it's a bond that's formed when two or more atoms share electrons. Okay. Due to the sharing, all atoms within a covalent bond are able to fill and maintain their full valence shells to both successfully have octets of electrons within their valence shells. The polarities of these bonds can be dependent on electronegativity, which is, the polar and nonpolar covalent bonds. These bonds are formed between atoms of nonmetals. Okay, so that's going to be on the right-hand side of the periodic table. Multiple covalent bonds can be formed between two atoms at a time, though. So we want to kind of identify what these bonds look like, how they're identified, and what's actually really going on. So when it comes to single bonds, let's say I have a carbon with 4 hydrogens around it, which turns out to be called methane later on. Whenever we have atoms that share one pair of electrons, what you see is that you see that there's one electron from the carbon that's being contributed and one electron from the hydrogen being contributed for each one. So since there's a pair of electrons for each two atoms, then there's only one bond happening. Each bond is equivalent to 2 electrons being shared, pretty much. So when I look at double bonds, if I take 2 carbon atoms with 4 hydrogens, okay, so the way it's going to do it is that they're still going to happen exactly what happens over here. The hydrogen only has 1 electron within its atom, so it has only 1 electron to give. So carbon forms single bonds with those hydrogens, but in between the 2 carbons, remember the carbons want to have a full octet too. They only have 4 electrons apiece. So the way that they compensate for this is that they share 2 pairs of electrons and they form what's called a double bond. So now there's 2 electrons from each carbon contributed to this bond. So since there's 2 pair of bonding electrons, it's called a double bond. And then we get to triple bonds, same thing. If I have 2 hydrogens, okay, they're going to form the exact same thing. They're going to form a single bond between the carbon and hydrogen on both sides. The carbon still wants 8 electrons around it. So to compensate for the 6 that it doesn't have, the carbons in between have to share 3 pairs of electrons. And that forms a triple bond. So there's going to be a bond here, here, and here. So when it comes to multiple covalent bonds and the sharing of electrons, there's another way the bonds are demonstrated within notation. So taking methane, we knew that we had those 2 pairs of electrons for each, the carbon and the hydrogen all the way around. Another way you'll see it is just a line. A line represents a single pair of bonding electrons or a single covalent bond. Okay? So again, this is where atoms share 1 pair of electrons. Then I have the single bonds from the carbon and hydrogens on the second example, and then the double bond that shows a share of 2 pairs of electrons is represented by 2 lines. So again, a pair for each line. So there's 4 electrons total being shared, but 2 bonding pairs, so therefore 2 bonds in between the carbons. Then the last example have the single bonds in between the carbon and hydrogens, and the 6 bonding electrons that we saw, the 3 pairs of bonding electrons, they represent 3 lines. So a pair here, a pair here, and a pair here. So that's what a triple bond is. Now, one thing that you may not notice, but is actually true, is that the more bonds that are present in between atoms, the shorter the distance there is. And what it is, it's kind of like tug of war. So if you have a long rope, which is like a single bond, you can be far apart. But if you fold that rope in half and you're still doing the exact same thing, you're going to get closer. And if you fold the rope again, you're still going to get closer. So the more bonds there are between atoms, the shorter the distance between those atoms are, which means that the shorter the distance, the closer those atoms become, which means the more unstable they are. So for example, this methane molecule that has single bonds is way, way more stable than this molecule over here, and is a little bit more stable than this molecule here with the double bonds. But then this double bond one is a little bit more stable compared to the triple bond. So, as the bonds become more present, the more unstable the molecule is 95% of the time. There are some exceptions, which we probably won't dive into this class, but there are some exceptions in regards to how like organic molecules form, so that other 5% is when that occurs. But for this class, just know that the more bonds you have, the more unstable it will become. So molecular and empirical formulas. We're going to dive way deeper into this next unit, but we're just going to kind of talk a little bit about it here. So a molecular formula represents the number of atoms of each element composing one molecule. So it represents the amount of atoms in each type of atom for one single unit molecule, not every single molecule, just one single molecule in itself. A molecular formula demonstrates only one molecule of the substance. A molecule is formed between the covalent bonds between atoms, which we've already kind of talked about way before in these other videos. So water is a molecule. Okay, so the molecular formula for water is H2O. Carbon dioxide is CO2. Glucose, which is sugar, is C6H12O6. Carbon monoxide is CO. So as you can tell, carbon dioxide and monoxide are really close to each other, both in name and in formula, but they're two distinct molecules. And we'll dive into how these names diverge here in just a second. And then we have dinitrogen monoxide, N2O. The next thing is the empirical formula. It represents the smallest whole number ratio of elements present within a molecule or compound. So it's taking the molecular formula and bringing it down to a more simpler level that we can describe a chain of molecules and other compounds together. Glucose, for example, the empirical formula for glucose is CH2O. The reason why is that between C6, H12, and O6, there's a common factor of 6. So if you divide all these numbers by 6, you simplify the subscripts to 1, 2, and 1. Okay? So the actual molecular formula for glucose that accounts for all the atoms present within one molecule is this. So if you look at glucose, it's going to have 6 carbons, it's going to have 12 hydrogens, it's going to have 6 oxygens. But if I was doing a more comprehensive look at the substance and I wanted to kind of break the substance into even smaller units and use the empirical formula, then I could use the empirical formula of glucose to kind of create those subunits. So that's the C1, H2, and O1. Water is H2O, but the thing is that 2 and 1, there's no common denominator between them. So water, actually, its empirical formula is its molecular formula because you can't reduce these numbers any further without turning them into decimals, which empirical formulas don't have decimal subscripts. Carbon dioxide, the same thing. It's a 1 and 2 ratio. You can't reduce it without turning those subscripts into decimals. So its molecular formula is also its empirical formula. And then dinitrogen tetraoxide, its molecular formula is N2O4. Well, there's a common multiple of 2 between these two numbers. So if I divide this by 2, it turns into NO2. Now, this looks like nitrogen dioxide, okay? But the thing is that the empirical formula for dinitrogen tetraoxide looks exactly like nitrogen dioxide, but they're completely two different things because nitrogen dioxide has a molecular formula of NO2, but dinitrogen tetraoxide has an empirical formula of NO2. So you have to be aware of what you're talking about and what type of formula you're talking about, okay? All right, so naming covalent molecules. The naming system for it it's completely different than ionic naming, okay? What it does is that the first thing you need to do is you need to take the first element present within the formula. That always goes first, okay? And then the first element includes a prefix that indicates the number of atoms present in the molecule. So that first element has a prefix in its name to indicate how many of that particular element is within the molecule. The first element does not need a prefix if there's only one. So that's the reason why on carbon monoxide, there's only one carbon, so you can just say carbon, okay? But if you have like that dinitrogen tetraoxide, there's 2 nitrogens in it, so you have to put a prefix in front of the nitrogen to demonstrate that there's 2 there. The second element follows in the second name as well. So, the second element that's in it follows second in the name as well. The second element also uses prefixes to demonstrate the number of atoms. So it also has a prefix to demonstrate how many of that same atom are in the molecule. But then what you do is you take the suffix off the second element and add IDE, like you would in ionic compounds. But it's not ionic. Okay, just be aware of that. Just because it has IDE doesn't necessarily mean it's the ionic compound. It's just how the naming goes. So the prefixes that are associated with covalent molecules you're going to have to memorize. So this is the chart of those. Okay, so you need to be able to memorize these and understand what they mean. So mono, not the disease, mono means a number of atoms of 1. Di means 2. Tri means 3. So some of these are a little bit intuitive. Tetra means 4. Then you get to these other ones. The other ones, depending on the atom that is present that these are being attached to, you may have either the basic root or the root plus the A. Okay, it just really depends on how they're called. There's not really a particular rule on when the A is added or not. So if you're writing the molecule and it sounds a little weird, just add an A to it and see if it sounds better, and that's probably what it is. So you have pent or penta, that represents 5. Hex or hexa, which represents 6. So like a hexagon that has 6 sides, you can think 6. Pentagon has 5 sides, you can think 5. Heptagon has 7 sides. Oct or octagon has 8 sides. Non or nona is 9, and then a decagon or deca is 10. Okay, so you need to memorize these as soon as possible, so that way, not only when it comes to quizzes or tests, but when you go into the next units, you know exactly how many atoms are in a particular molecule, because if you don't, then your calculations and stoichiometry are going to be way off, and you're not going to know what's going on there. So a couple examples. We'll kind of just do a few examples together. So carbon monoxide. We've already seen this before, but let's break it down. So we know that the first element is going to be carbon, which is C. There's nothing in front of it, which means there's only one of that element. So we're going to have one C. And then I know oxide is oxygen, okay, with IDE on it. But I know mono represents 1. So then I have one carbon and one oxygen. So I just put them together. You get CO, okay? That's big C, big O. Then you have pentaphosphorus trinitride. Okay, so penta means 5, phosphorus, so 5 phosphorus, and then tri, 3. Nitride is nitrogen. Okay, so you have 5 phosphorus and 3 nitrogens. So you have 5p3n. Then you just put them together with their subscripts, p5n3. That's it. Dihydrogen monoxide. Okay, so I have 2 hydrogens because of the di. And then monoxide, which is oxygen, mono meaning 1. Okay, so that means I have 2 hydrogens and 1 oxygen. Yes, it's also called water. Okay, it's H2O. So the chemical formula name for water is dihydrogen monoxide, but you're never ever going to hear that. Okay, unless it's in a joke. Everybody, including scientists, call it water. So, but technically it does have another chemical formula name if you want to use it. Disulfur decasilicide. So di meaning 2, sulfur, so I have 2 sulfurs. Deca meaning 10. Silicide is silicon. Okay, so I have 2 sulfurs and 10 silicons atoms. So it turns into be S2Si10. Okay, a pretty big molecule. Yes, you can make this. I'm not making it up. Dichlorine heptaoxide. So I have 2 chlorines because of the di. Hepta meaning 7. So you can see that there's an A here. So if you put heptaoxide, that sounds weird. So I added an A and it says heptaoxide. It flows a little bit more naturally. So it means 7 oxygen. So I have 2 chlorines, 7 oxygens. Chlorine is first, so I put the chlorine and the oxygen together. Now you're probably saying, well, they're both nonmetals, but they form anionic charges. That's true. But the thing is that this is not an ionic bond. So you can put 2 nonmetals together without forming an ionic bond. They just have to share a different number of electrons based off the type of bonds that they have to maintain that neutral charge. Nitrogen monoxide. So again, we have nitrogen does not have a prefix in front of it, so we can assume there's 1 nitrogen. And then monoxide, which we've already seen before, is 1 oxygen. Okay, so you just put them together. It's just NO. Carbon tetrabromide. Carbon doesn't have a prefix, so there's only 1 carbon in it. Bromide is from bromine. Okay, and tetra means 4. So I have 1 carbon and 4 bromine atoms. So it's just CBr4. Carbon mononitride, 1 carbon, 1 nitrogen. This is also called cyanide. You've probably heard of this before, so it's a cyanide. Cyanide typically has a negative charge to it too, but if you see CNs, it'll say it's cyanide. Nitrogen trihydride. That's going to be 1 nitrogen molecule and 3 hydride. So this is hydrogen. Okay, so it's now you're probably asking, well, hydrogen's on the left-hand side of the periodic table, isn't it supposed to have like metal-like qualities? Well, it can, and this is the weird thing about hydrogen. It can act as both a metal and a non-metal. So hydrogen's really cool in that sense, but it can be both covalently bonded and ionically bonded to things. So just be aware of that. So nitrogen trihydride is 1 nitrogen and 3 hydrogens. This is also called ammonia, the gas of ammonia that you can smell from like cleaning supplies and stuff like that. That has a formula of NH3. And then you have tetraboron heptaiodide. Okay, so tetra meaning 4, boron, so B, hepta meaning 7, iodide meaning iodine. Okay, so that's in the halogen group. And so you have 4 boron, 7 iodine, so you have B4I7. All right, so that's the end of this video. Again, a lot of information to take in. It only comes from practice. So the more you practice this, the better you get at it. Okay, so if you have any questions, please come talk to me. Talk to a friend if you need to. Whatever you need to do to understand this material. Because if you don't get this unit, you're not going to get the next units. Trust me. So again, thanks for watching this video, and I hope to see you in the next one, and see you in class. Bye.